Okay. Okay, good afternoon, everybody. This is a session, harmonic analysis, fractal geometry and applications. And I want on behalf of the session organizers, welcome everybody and thanks the speaker for accepting giving a talk here. Just some instruction. After the talk, there is going to be some time for 1 or 2 questions. So please try to keep your comments or questions for the end. But if somebody needs to interrupt, just in the middle of the talk, just send the question by chat, and the chairman will decide what to do, if interrupt the speaker or not. So today we have a very exciting program. So I hope you enjoy the talks. And I leave you now with Pablo Smarkin that will chair this part of the session. Thank you very much. So Pablo.
Oh, sorry, I was muted. Okay, so welcome. Nice to see you, everybody. So Kathryn, do you want to show your slides? I don't know if she's a co-host.
Yeah.
Okay, I'll share my screen. Okay.
Perfect.
Okay, yeah, sounds good. So the first talk is by Kathryn Hare from the University of Waterloo here in Canada. And as you can see, she's going to tell us about local dimensions of similar measures with overlap. Go ahead, Kathryn.
Well, thanks. Thanks you to the organizers for inviting me. I'm going to be speaking about joint work with my colleague, Kathryn Hare. I should say he is no relationship whatsoever. It is entirely coincidental that we have the same last name. And this is also work with our recent student, Alex Rutar. So what we're interested in is trying to understand more about the structure of singular measures. And for me, a measure is going to be a Borel probability measure on the real line. And my slides are not scrolling for some reason. So when I say singular, I will mean with respect to Lebesgue measure. And so we're talking about measures that live on or concentrated on sets of Lebesgue measure 0. And what we're particularly interested in is understanding the concentration level of the measure and how it might vary as we move around the support of the measure. One way that one can quantify the concentration of a measure is by what's known as the local dimension. These are numbers that we could try to compute at each point in the support of the measure. And I'm denoting it by dim mu of x at the point x. And the way you would compute this is you take the mu measure of the interval centered at x, radius r. You take log of that interval, log of that measure, divide by log r, and let r go to 0. Now, of course, the limit might not exist. We might want to take a lim inf for a lim sup, and then we're talking about a lower local dimension or an upper local dimension. But for the purpose of this talk, I'm going to stick to the case of the dimension existing. So one example of a singular measure on R is going to be one that's well known, I think, the Cantor measure on the classical middle third Cantor set. So what I mean by this, sometimes called the uniform Cantor measure, is the measure that will assign to each of the intervals that arises at step n in the usual construction of the Cantor set, those intervals of length 3 to the minus n, it's going to assign each of those intervals mass 2 to the minus n. And this measure is well called uniform because in particular, its local dimension is the same everywhere. It's simply log 2 over log 3 at every point. So that's not very exciting. But if we bias the measure, then we can see something more interesting happening. So by a biased measure, what I'm going to call a p-Cantor measure, where p will be a number between 0 and 1. And actually, the case p equals a half is the uniform case. So the way this measure will work is that if you take one of the intervals that arises in the usual construction of the Cantor set, course, it will have two descendants at the next step. And the left descendant, or the left child, is going to get measure P times that of the parent, and the right child will get measure 1 minus P times the measure of the parent. So P is not a half. You can see this measure does not look the same everywhere. And this is certainly reflected again in the levels of concentration, because what happens now is if you look at the attainable local dimensions as you let X run over the Cantor set, which is the support of the measure, it is going to be an interval of numbers ranging from log P over log a third to log 1 minus P over log 1/3, where these are actually the local dimensions. These endpoints are the local dimensions at the two ends of the support of the Cantor measure. And the fact that you get an interval here of local dimensions, I think is very natural, because although these are singular measures, they are examples of continuous measures. That is, the measure of every singleton is 0. And so it's nice to see that their concentration levels change across a continuum. Well, this is really a special case of a much more general situation where we start with an iterated function system, a finite family of similarities, maps Sj of the form Rjx plus Dj that are contractions, and associated probabilities, positive numbers Pj that add to 1. And anytime you have a setup like this, then there is always going to be a unique non-empty compact set K, which is invariant under these maps Sj in the sense that I've written here, sometimes called the self-similar set associated with the iterated function system. And similarly, again, an application of Bonnet contraction mapping principles shows that there is a unique probability measure mu, which is also invariant under the maps Sj and the numbers Pj in the sense that I've written here, called a self-similar measure, and it will have as its support the self-similar set K. The case of the Cantor set and the P-Cantor measures are the special case where we start with the two functions x over 3 and x over 3 plus 2/3. That will give us the Cantor set as the self-similar set. And then if we take the two probabilities to be P and 1 minus P, the measure that comes out would be the P-Cantor measure. Now, these Cantor measures have another special property, and that is if you take the interval 0, 1, the convex hull of the Cantor set, and you apply these two maps, what you're going to get are the two intervals that come up at step 1 in the construction. Of course, they're supposed to be the same length, 0, 1/3 and 2/3, 1. But the point is that there's a gap between them. They're well separated. And when you have a separation property kind of like that, called the open set condition, it is always the case that the self-similar measure that arises has the property that the set of local dimensions that are obtained is always a closed interval. What I'd like to talk about in this talk then is what happens if you have an IFS that does not satisfy the open set condition. And that is what I meant by measures with overlap in the title of the talk. So first of all, let me mention some examples of measures with overlap. There are many interesting examples. One much studied family are what are called the Bernoulli convolutions. These are the measures that arise again from an IFS with two maps, Rx and Rx plus 1 minus R. But this time, instead of R being 1/3, we take R more than a half. And we use the probabilities 1/2, 1/2. So what's going to happen here is the self-similar set is actually a full interval 0, 1. And you notice that when you apply these two maps to the interval 0, 1, well, you're going to get an interval 0 to R and another interval 1 minus R to 1. And because R is more than a half, these intervals strictly overlap. And so the open set condition fails. But even though the self-similar set is an interval, these measures can still be singular. And this was observed by Erdős more than 80 years ago, when he found that if you take the contraction factor R to be the inverse of the Pizot number, so a special kind of algebraic number, then these measures will be purely singular. Since that time, there's been very extensive research done on trying to understand which Bernoulli convolutions are singular and which are absolutely continuous. They will always be either one or the other. And thanks to work of people like Hoekman and Pablo, we now know that most of these Bernoulli convolutions are actually absolutely continuous. But it remains open today whether or not the examples that Erdős found more than 80 years ago are the only singular examples. So Fang looked at the study of the local dimensions for these measures in the case when R is the inverse of a simple Piso number. So a special kind of Piso number, but there are still infinitely many of these. And he found that for all of these measures, despite the fact that the open set condition fails, we still get a closed interval as the set of attainable local dimensions. So that's one interesting family of examples. Another family of examples are the measures that arise if we start off with the uniform Cantor measure and then convolve it with itself some number of times. It doesn't matter how many times you do the convolution, you will always get another self-similar measure. You need more contractions as you take more and more convolutions, and you have to choose the probabilities properly. Once m is at least 2, it turns out that the support of the measure is actually the full interval 0m, but in all cases, these are purely singular measures. And the open set condition only holds for m equals 1 or m equals 2. It fails as soon as m is 3. But these are still very nice measures. And the fact that they arise as a convolution, well, I mean, convolution is an averaging process. There's sort of a general rule of thumb that things get nicer as you convolve. And so I think people were pretty surprised when Hu and Law, it was about 20 years ago now, discovered that if you take the threefold convolution, mu star mu star mu, so the first time the open set condition fails, the set of local dimensions that you get for this measure is not an interval. It consists of an interval and a single point, which is strictly to the right. This point being the local dimension at the two ends of the support of the measure, 0 and 3. So, what is going on here? Why is it that with our Bernoulli convolutions, which fail the open set condition, we get an interval of local dimensions, but this convolution of the Cantor measure three times, a very nice measure, and we fail to get that very natural property holding. So what I'd like to talk about is a general theory that we have been developing that will perhaps explain at least some of what's going on here. So our basic setup is that we have an IFS of similarities, Sj, probabilities, Pj. I will assume without loss of generality that the self-similar set has convex Hall 0, 1. This is without loss of generality because we can always rescale if we need to. Because of the time limitations, I'm not going to be able to define things precisely, but I hope that I will at least give you a flavor for what's going on. So just a bit of terminology first. If I'm given a word, sigma 1 through sigma n on the letters 0 through m, then when I write S sigma, I will mean the composition of the maps S sigma 1 through sigma n, and R sigma will be the contraction factor of S sigma, the product R sigma 1 through R sigma n. And I'm going to say that the word sigma is of generation T if its modulus is approximately T. Okay, so the two really important ideas are net intervals and neighbor sets. So by the net intervals of generation T, what I mean are the little subintervals that arise when I take my interval 0, 1 and consider all the subintervals that are formed by using the points S sigma of 0 and S sigma of 1, where sigma runs over all the words of generation T. And actually, we only take the little subintervals that contain points of the self-similar set in its interior. So those will be the net intervals of generation T for T less than 1. And the full interval 0, 1 will be the net interval of generation 1. And these intervals themselves, they will, of course, decompose at a later generation. And so we can talk about their children or their grandchildren and so on. And by the neighbor set, well, because of the definition of the net intervals, each net interval of generation T is going to be contained in certain of the images S sigma of 0, 1 for sigma of generation T. The neighbor set is going to be all of those maps S sigma with this property here, where we suitably normalize them, right, to take into account in some way the generation. So the neighbor set is going to be a certain collection of normalized maps S sigma, where S sigma of 0, 1 covers delta. And we're going to say that the iterative function system satisfies the finite neighbor condition if there are only finitely many neighbor sets, finitely many distinct neighbor sets in totality. Now, you might be thinking, how could this ever be? After all, there are going to be new net intervals arising at each new generation. But remember, we are in a self-similar situation. And so we do expect to see the same kind of geometry being repeated over and over again, just at different scales. And our normalization that we put on the neighbor set, we'll take that into account. And so, in fact, this property is actually very prevalent. It holds anytime we have an IFS that satisfies the finite neighbor condition, but also many that do not. In particular, all of these Bernoulli convolutions that we talked about, if the contraction factor is the inverse of a Piso number, have this finite neighbor condition. For instance, if you take the Piso number to be the golden mean, there are 6 neighbor sets. All of the M-fold convolutions of the Cantor measure have the finite neighbor condition. Tested looked at some interesting examples of IFS. His examples all have the finite neighbor condition. His examples are, well, the one I've written down here is very typical with contraction factors plus and minus a quarter. That one has 2 neighbor sets. In fact, as far as we are aware, every example in the literature of an IFS that satisfies the weak separation condition actually has this property, the finite neighbor condition. If you don't know what the weak separation condition is, you just think of it as kind of some modest control on the overlap, without which it's very hard to do very much. So it's a very rich family of examples, and it's very possible that the finite neighbor condition and the weak separation condition actually coincide. This neighbor set turns out to carry for us most of the important geometry about this IFS. And in particular, if you have a net interval, and it will of course have some children, the neighbor set of the net interval really gives us all the information we need about the children, including how many there are, what their neighbor sets are, and so on. And so we can encode this information in a graph where the vertices are neighbor sets, and we have an edge joining a parent to a child. If we have multiple children with the same neighbor set, we'll have multiple edges. And from here on, I'm going to assume the finite neighbor condition is satisfied. So that will mean this transition graph is finite. And I think of the neighbor set of 0, 1 as the root vector or the origin of the graph. Every finite path that starts at the origin is actually in a 1-to-1 correspondence with a net interval. Because if you start a path at the origin, it will go from 0, 1 to a particular child and then to a particular grandchild and so on. And so it will just descend down to a particular net interval. And you can just lift back up for the converse. And similarly, every point in the self-similar set is associated with an infinite path starting at the origin, a path that will have a nested sequence of net intervals containing the point x. But this might not be a 1-to-1 correspondence, because if a point sits on the boundary of 2 net intervals, then there could be 2 paths coming to it, one coming from each side. But that's the only way you get a non-unique path. And we call these paths the symbolic representation. Well, here's a picture of what the transition graph looks like in the case of the Bernoulli convolution with the golden mean. I said there were 6 neighbor sets. 1 is the origin. And then you see it has 3 children, 2, 3, and 4. 2 has 2 children. One of them has neighbor set 2 again, and the other neighbor set 3, and similarly with 4. 5 here has 3 children. One of them is neighbor set 6, and 2 of them are neighbor set 3. Now you're probably wondering, how does this relate back to the measure? Well, there's one more idea we need, the transition matrix. To each edge in the graph, we're going to associate a matrix. Now, remember, an edge is going from a neighbor set of a parent to the neighbor set of a child. And basically, this matrix tells us how the measure is passed from the parent to the child. It turns out it only depends on the neighbor set. So this is well defined. And then if we're given a path eta, just going to be a sequence of edges, we define the transition matrix of the path to be the product of the transition matrices of the edges. And the connection, which I think was perhaps first observed by Feng in this special situation, is that if you have a net interval with whose symbolic representation is the path eta, then the measure of that net interval is comparable to the norm of the matrix, the transition matrix T of eta. Where here the norm is the usual norm on matrices, sum up the absolute values of the entries. And comparable means that there are universal positive constants, so that mu of delta is bounded above and below by those constants times the norm of the transition matrix. Now remember the way that local dimension was defined. We were supposed to take the mu measure of the net interval centered at x at radius r. If we could replace these centered intervals by the net interval containing x of about size r, we would be in a very good position, because knowing this measure up to comparability is going to be good enough. When you take logarithms and you let r go to 0, the constants that bound this as a multiple of the matrix norm of T of eta, they get washed away when you take the limit. And so if we could simply replace centered intervals by net intervals, we'd be able to compute the local dimension. But of course, you cannot do that without some care. I mean, what would happen, for example, if your point x was a boundary point of 2 net intervals of size r? Then your centered interval will contain both of them. Even worse, what if your point x is close to, but not right on the boundary? Then the centered interval is going to contain a good portion of the adjacent net interval as well. So we certainly have to be careful. It turns out that the case when the point x is a boundary point is actually very easy to manage, because when it is a boundary point of a net interval, it is a special kind of point. We call it a periodic point. This is a point whose symbolic representation starts off with some initial path, that then it becomes a cycle that's just repeated over and over again. Whenever you have a periodic point like this with a unique symbolic representation, there's a simple formula for computing the dimension. You take the spectral radius of the transition matrix of the cycle, logarithm of that, and then you divide by this number w of the cycle, where just think of w as a function that generalizes generation to paths. And this is a very nice formula because it does not require taking any limits, because we can get the spectral radius of the matrix simply as the maximum of the eigenvalues of the matrix in absolute value. So that's what happens if you have a unique symbolic representation. But if you're a boundary point of a net interval, you quite likely have 2 symbolic representations, but then they were both going to be periodic in this sense. And so we compute this ratio in both cases for both cycles, and the smaller of the 2 is the local dimension. So that does the boundary case. The non-boundary case is actually more subtle. And before I go into that, I just want to point out a few other things about this transition graph. And this is typical of what we see. You notice there's a couple of loops in this graph. There's a loop here at 2. We can go from 1 to 2, and then we can stay at 2 forever. That infinite path actually takes us to the point 0. We have another loop here at 4. We can go 1, 4, 4, 4, 4, stay at 4 forever, and that takes us to the endpoint 1. And we have another loop here, 3, 5, 6, which we can go around in many different ways. The loops at 2 and 4 are simple loops. The 3, 5, 6 is not. They are all maximal loops. That is, we can't adjoin any other vertices to them and still be a loop. And we always see this in these transition graphs. Every infinite path that starts at the origin is going to have to eventually fall into one of these maximal loop classes. Basically, that's because once you exit a maximal loop class, by definition, you could never return to it. And there can only be finitely many of them since these are finite graphs. So every infinite path belongs eventually to some maximal loop. And so we can also say that every point in the self-similar set belongs to some maximal loop in the sense that its symbolic representation is eventually in that maximal loop. Now, a point might then be in 2 maximal loops if it has 2 symbolic representations. Okay, so with this terminology in mind, here is our main theorem. Suppose that L is any maximal loop class which is not simple and is irreducible. It's a technical condition I'll say a bit about in a moment. In that case, when you take a look at the set of local dimensions that are obtained by taking all the points which have a unique symbolic representation, which is eventually in that loop class, maximal loop class L, that is a closed interval. And the endpoints of this interval are these numbers alpha min, alpha max that I've written down here. So again, they involve the transition matrices. And you taking a limit, you have to work those numbers out. But the point is, it is always a closed interval. And that's if you have a unique symbolic representation, which certainly includes all of the non-boundary points. They all have to have unique representation. When you put these two results together, here is the corollary that you get. So we have an IFS that satisfies the finite neighbor condition. It will have only finitely many maximal loop classes. Let's list them from 1 to n Li. And we will assume that each maximal loop class is either simple or irreducible. In that case, when you take the set of local dimensions as you let X run through the entire self-similar set, the support of the measure, this will be a finite union of closed intervals. These are the intervals given by these numbers that I had in the previous theorem. We can compute these numbers for simple loop classes as well. They happen to be equal, these two numbers in that case, so the interval becomes a single point. And I put an n prime here rather than n because it's possible that some of the simple loop classes might not appear in this union. That's because a simple loop class just comes from a cycle, and it might be that the points have a second symbolic representation and they get their local dimension. Remember, it was a minimum of 2 choices from the other loop class. So some loop classes might be excluded, but all of the non-simple ones are there. And what is irreducible? Well, as I said, a technical condition, it's a positivity requirement on the collection of transition matrices from the loop class. It's simply a geometric property of the IFS, has nothing to do with the probabilities itself, just the contractions. And again, it seems to be, well, this is a kind of condition that's been used by other people, sort of condition used by other people looking at this type of problem as well. And it seems to be very, very prevalent. We actually do not know of any IFS satisfying the weak separation condition that does not satisfy the hypotheses of this corollary. Every example we're aware of that has the weak separation condition has the finite neighbor condition, and it has the property that all of the maximal loop classes are either simple or irreducible. Perhaps irreducible is simply automatically satisfied. We don't know. So let me just finish up by going to our classes of examples we looked at the beginning and what is happening there. With the Bernoulli convolutions, with our simple piezo inverses as contractions, or the m-fold convolutions of the uniform Cantor measure, and not just on the middle third Cantor set, but middle fourth or fifth or whatever, there are always 3 maximal loop classes, 2 of which are simple, correspond to the 2 endpoints, and one which is not simple and is irreducible. So it generates an interval of local dimensions. In the case of the Cantor convolutions, the dimensions at 0 and 1, which will coincide, are not in the interval generated by that other maximal loop class. And that is why in those examples, we will always see an interval and an isolated point. But in our Bernoulli convolution, again, the dimensions at 0 and 1 coincide, and it just so happens that that number is the upper end of the interval generated by the non-simple maximal loop class. But interestingly, if you replace the uniform Bernoulli convolution, so half-half, with P1 minus P as your probabilities, with P naught 1/2, you will always get an isolated point in the set of local dimensions. And what happens is that as P moves towards a half, both the point and the interval itself move, and they move together so that in the limit, they just touch. And that's why you do not see an isolated point. I think maybe it's a fluke in that sense. The test stud example, there are two maximal loop classes in this example. Neither of them is simple. They are both irreducible. So they both generate non-trivial intervals of local dimensions, and you can choose probabilities so that these two intervals are disjoint. And so what you can see, and you can see examples where you get two disjoint closed intervals, non-trivial intervals, as your set of attainable local dimensions. We speculate that it should be possible to get any number of disjoint closed intervals, possibly some of which are singletons, degenerate intervals. Yeah, we think it should be possible. You could get a lot, perhaps as many as you have maximal loop classes, considering this corollary. But to be honest, we don't have any evidence for that speculation because we have not been able to produce examples with more than two. But we don't see any reason why that shouldn't be possible to do that. It's a very difficult problem to produce examples. So I think I should probably stop here because I'm pretty sure my time is over. So thank you again for inviting me.
Yeah, thank you, Kathryn. This is a very nice talk, and actually my licenciatura thesis with Ursula was on this topic many years ago, of course, so it's nice to see that there is so much progress and so much better understanding now. So we have time for maybe one or two quick questions. So are there any questions?
Hello, Kathryn. I'm Chinke. Thank you very much for your talk. I like your talk. And I have a question which is related to my study of Fourier frame for many years. It's about local dimension. Under those finite type conditions, do we have any self-similar measure whose local dimension has only one, except those with open set condition? Those with finite type and no open set conditions, do we have local dimension?
Only one value attained is the set of local dimensions?
Yes, it's a singleton.
I think so. I certainly can think of examples where there are precisely two. You can even do that with convolutions of Cantor measures. You just make the right choice of numbers of convolutions and the contraction factor. Just one number. I'm pretty sure that there are examples, but I can't think of any off the top of my head because it is possible for the,
Anything.
you know, with choices of probabilities to make those intervals degenerate.
Yeah, degenerate up to one, only
Yeah.
one.
So you'd have to, yeah. It does seem to be hard though, doesn't it? Yeah.
Okay.
But certainly two points is
2
certainly possible.
Okay. Thanks.
Well, maybe I'll ask a very quick question. So is it possible that for all self-similar measures, without assuming any separation, the set of local dimensions is a finite union of intervals? is that a plausible conjecture? Possibly very hard to prove, but is it possible?
Yeah, well, we certainly don't have any examples to the contrary. It seems natural that it would be like that. But I have no idea on that. If you don't have some structure, it's hard to get a grab on
Sure.
these things. But that would certainly be a very nice result to get.
Okay, so I think it's time to prepare for the next talk. So let's thank Kathryn again.